The exponential distribution is a new continuous distribution, and it corresponds to a random variable that we motivated as saying the time between rarely occurring events. Now, the density function for this is given by this exponential, and it has the following density curve. A couple things that I want to note. When we talk about f of x, we are talking essentially about the antiderivative, the one antiderivative of this density function that starts at 0 and ends at some value of x. And so this density function measures the area, the CDF gives the area under this density curve f of x. So that's visual idea number one. And more of an interpretation here, when we've got our density function the way we do here, you can interpret the graph as follows. These are our outcomes x. If we are using the exponential distribution to model times between rarely occurring events, sometimes we treat this as a model for failure times. Failure times means how long does it take before this rare event occurs or some object fails. If you take a look at the density curve, spots in the density curve where you have a higher graph means it's more likely to fail at these times. And by these times, I'll shade down here. Whereas when you have a very low graph, it is less likely to fail at these times. And that kind of makes sense, right? You don't expect an object to fail after a very, 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 very long time. It's probably going to fail sooner rather than later. So these infinite times wouldn't really happen. Now, I've said that the exponential distribution is a model to use between rare events or a model to use between Poisson events. So I'm going to talk about the example that's on the PDF file attached to this video to do with the imperfections. So the imperfections in an optical fiber are distributed according to a Poisson process. And we have been told that this distribution rate is essentially two imperfections per meter. So the distribution, if we say that capital X here is the number of imperfections, and we will put something definite, and we'll say it's the number of imperfections in a 3-meter stretch, we know from our past experience that this random variable is going to be modeled by a Poisson distribution where it's lambda times 3, or in this case, a Poisson distribution of 6, because the lambda that we've been given here is 2. So the number of imperfections is modeled by a discrete random variable. And once you've got that, it's easy to answer some questions. So for instance, what's the probability that we will have no more than 4 imperfections in a 3-meter stretch? That's essentially a CDF question. And in the discrete sense, it's adding up the probability for each one of these discrete outcomes. We know how this works for a Poisson distribution. And in particular, we know that this lambda times x is going to give us 6 here. So it's a relatively simple matter to calculate this. Now, you can calculate this using P Poisson in R. So you would say P Poisson 4, 6, and you would end up getting an answer of about 2.851. So there's about a 28% chance that you will see 4 imperfections in 3-meter stretch of this wire. So that's nothing new. That all relates to the discrete random variable that we talked about before. But now, if we let y be the distance between imperfections, that means we are essentially talking about a continuous random variable. This is a different variable. It measures the space between these imperfections. From earlier, this is going to be modeled by an exponential distribution with a parameter of lambda. And that comes from our derivation that we had from earlier. And so, in this particular case, in this particular case, this is an exponential distribution with the parameter of 2. If we wanted to then do some calculations, so for instance, what is the probability that the distance between imperfections is greater than 1 meter? That means we are asking this question, the probability that y is greater than 1 meter. Now, in a continuous random variable, there is absolutely no difference between saying greater than 1 meter or less than or equal to, greater than or equal to. So in this sense, we don't have to be too worrisome, but where it's advantageous for us to use strictly greater than is because now we can turn this into a CDF problem, which is really our goal. The mathematical tool that we have here is the CDF. And that means this is essentially just the CDF of the exponential distribution. And once we have that understanding, it's very straightforward to use the CDF because we know that it's going to be 2 times our value of 1 in this case. The CDF is 1 minus e to the negative lambda y in this particular case. So we'll get e to the minus 2, and this is about 0.1353. So it's very straightforward to calculate problems using this exponential distribution. And if we wanted to know the expectation of the distance between these imperfections, that's like saying calculate the expected value of y. From the result we had earlier, it's just 1/2. So in this sense, I'm hoping that you can see the connection between the random variable y, the new continuous one that's in an exponential distribution, and its counterpart, I suppose you could say, in the discrete case with the Poisson variable.